In this video, we're going to use the unit circle to talk about sine and cosine. So the unit circle is a circle of radius 1 centered at the origin. And every point on the unit circle is an ordered pair x comma y, which satisfies x squared plus y squared equals 1. X squared plus y squared is equal to 1 is the equation of the unit circle. Now we're going to define something called the wrapping function on a unit circle. The wrapping function has an input of an angle, and the output is the point that the terminal ray intersects the unit circle. The notation we're going to use for the wrapping function is capital W of angle theta is equal to the point x comma y. So here's what it does. We take an angle whose initial ray is along the positive side of the x-axis and whose terminal ray is somewhere. And wherever that terminal ray hits the unit circle, that point is going to be the output of the wrapping function. It turns out with this wrapping function, we can define cosine of theta and sine of theta on the unit circle. Simply put, cosine of theta is the x value of the wrapping function, and sine of theta is the y value of the wrapping function on the unit circle. So we get this picture here. Now, if you think about it, since cosine of theta is the x value, it is also the distance from the origin to this right angle here on the unit circle. And since the sine of theta is the y value, it's the distance from this right angle up to the point on the unit circle. And so every time we're on the unit circle, we have a triangle whose hypotenuse is of length 1, since the radius of the unit circle is length 1. So that's how we can define cosine of theta and sine of theta on the unit circle. Now, one interesting thing this gives us is something called the Pythagorean identity. Since the equation of a unit circle is x squared plus y squared equals 1, in other words, since each x, y point on the unit circle satisfies that equation, and we know that the x value can be represented with cosine of theta, and the y value can be represented with sine of theta, we get that cosine squared of angle theta plus sine squared of angle theta is equal to 1. And we'll use that a little bit later. So let's do some basic calculations given what we know about the unit circle and angles. Let's come up with the wrapping function output, which will give us the cosine theta and the sine theta for various angles on the unit circle. Now, these angles are going to be in radians. So we're going to use 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. You can also use degrees, but I'm not going to in this example. So let's try to fill out this table. We're going to start with angle 0. So when theta is angle 0, where is the wrapping function point? And what does that mean cosine of 0 and sine of 0 are? So let's look at a picture of the unit circle. If we're at angle 0, then my ray is shooting along the x-axis. And we end up hitting the point 1, 0. Therefore, the output of the wrapping function when the angle is 0 is going to be the point 1, 0. So here I've written that on the table. The wrapping function at angle 0 is the point 1, 0, which means cosine of 0 is equal to 1. That's for the x value. And sine of 0 is equal to 0. That's the y value. We can do a very similar thing with pi over 2. If you look at the unit circle, pi over 2 would give me a terminal ray shooting straight up. Pi over 2 is 90 degrees. And obviously that hits the circle at the point 0, 1. For pi, our terminal ray would be shooting straight to the left on the x-axis, and therefore our terminal ray would hit the point -1, 0. For 3 pi over 2, our terminal ray would be shooting down, and we'd be hitting the point 0, -1. And for 2 pi, we'd be back shooting in the positive direction along the x-axis, and we'd be back at the point 1, 0. So let's fill out this table based on what I just said. So wrapping function of pi over 2, remember pi over 2 is 90 degrees. That's going to be 0, 1, which means cosine of pi over 2 is a 0, and sine of pi over 2 is a 1. The wrapping function at pi is 180 degrees. That's going to be the point -1, 0. And so cosine of pi is going to be -1. Sine of pi is going to be 0. 3 pi over 2, the wrapping function, that's 270 degrees. That's pointing down along the y-axis. That is 0, -1. And so cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. And then once we've gone fully around the circle one time, 360 degrees, we're actually back at the point 1, 0 again. So cosine of 2 pi is 1, and sine of 2 pi is 0. Obviously, the wrapping function at 0 and the wrapping function at 2 pi have the same output. So cosine and sine at 0 and 2 pi will have the same output. Now, those values for cosine and sine were fairly straightforward to find because we knew they were along the x and y axis. So what if we want to find some other angle, some angle that is not along the x-axis or the y-axis? Can we find these values for angles not on one of the axes? And it turns out we can in a lot of different ways. One way we can find wrapping function values, which are going to be cosine and sine values, is to use triangles. We can do that with 30 degrees, which is pi over 6 radians, 60 degrees, which is pi over 3 radians, and 45 degrees, which is pi over 4 radians. Essentially, I'm going to use the triangles here that we have on this diagram to come up with the wrapping function values. So let's start with the 45-degree case. So if we have the 45-degree case, then this triangle is going to have a 90-degree angle down here. And since the angles of a triangle have to add to 180 degrees, that means both this upper angle and this lower angle are going to be 45 degrees. So that also means that if this length is x, then this length also has to be the same. Since those two angles across the way are the same, this is an isosceles triangle, an isosceles right triangle. So the two legs have to both be the same distance. And that means that if I want to go and find the x value, I can do that utilizing the Pythagorean identity or the equation of the unit circle. I'll just talk about the equation of the unit circle in this case. So I'll write it as x squared plus y squared is equal to 1. Now we know that both the x and y values have to be the same. And therefore, so again, the x and y values have to be the same. Therefore, I can replace this y with an x. So I can get x squared plus another x squared is equal to 1. And that's an equation that I can solve for x. So let's go ahead and solve that for x. We'd end up with 2x squared is equal to 1. Dividing both sides by 2 would give me x squared is equal to 1/2. And then I can take a square root of both sides. If I take a square root of both sides, first off, I should say x has to be positive because it's going from 0 to the right in this diagram. So x is going to be positive. I'll take the positive square root. When I take the square root of both sides, the positive square root of 1/2 is going to be 1 divided by the square root of 2, which, if you want to rationalize the denominator, is the square root of 2 divided by 2. Okay, you just multiply by square root of 2 on top and bottom. So what's that mean for my wrapping function? That means my wrapping function has x value of the square root of 2 divided by 2. And since the y value and the x value have to be the same, then the y value also has to be the square root of 2 divided by 2. And since we know that that is the cosine of the angle, the x value is the cosine of the angle pi over 4, and we know that the y value is the sine of the angle y over 4. Now I know that the cosine of pi over 4 radians, or 45 degrees, is equal to root 2 over 2. And I know that the sine of pi over 4 radians, or 45 degrees, is also root 2 over 2. So I get that by observing that this creates an isosceles triangle when I have a 45-degree angle as my theta. Now, what if this angle happens to be 60 degrees? I've drawn the 60-degree angle right here. Obviously, we don't have an isosceles anymore, but is there a clever way to get around this? And the answer is yes. If we have a 60-degree angle, because of the fact that this is 60 degrees, the complementary angle would be 30 degrees. That's the angle in here. If I draw another 30-degree angle, what I end up with is an equilateral triangle. So 30 plus 30 is 60. I'd get an equilateral triangle right there. Since we have an equilateral triangle, I know that the equilateral triangle has all three sides the same length. Again, I know it's equilateral because this is 60 degrees. This was 30. I doubled that. And so this is also going to be 60 because the angles of a triangle have to add up to 180. Because it's equilateral, each of these side lengths has to be the same. And that means if we take the distance from the origin to halfway through the side, this distance is going to be 1/2. Notice that that is the x value of the output of the wrapping function. So that gives me the x value for my wrapping function as 1/2. I can find the y value by using the equation of the unit circle, or the Pythagorean identity if I wanted to write it in terms of cosine and sine. Now that I know the x value is 1/2, I'd take 1/2 squared plus y squared is equal to 1. 1/2 squared is 1/4. So we'd end up with 1/4 plus y squared is equal to 1. Excuse me, hit the wrong button. Subtract 1/4 from both sides, and we get y squared is equal to 3/4. Again, we can see on this picture that since the y value in the Cartesian coordinate plane is moving up, we know the y value is positive, so we can take the positive square root of both sides and find that the y value is equal to the square root of 3 divided by the square root of 4, which is 2. So the y value is root 3 over 2. So that's the wrapping function of 60 degrees or pi over 3 radians. And that means that the cosine of pi over 3 radians has to be 1/2, and that the sine of pi over 3 radians has to be root 3 over 2. All right. Now, with that, notice that this triangle was a triangle on the unit circle with a 60-degree angle at theta. So a 30-degree angle was its complementary angle. If I just rewrite this or redraw this for the 30-degree angle, what I'd be doing is essentially I'd be down here. I didn't do this very well, excuse me. If I did this for a 30-degree angle, what would happen is I would get something like this triangle. And once again, we would see that since it's a 30, 60, 90 triangle, I can add a couple of sides and then create an equilateral triangle. But this time the y value would be 1/2. And then based on my algebraic work, the corresponding x value would be root 3 over 2. So what we're saying there is that if we sort of copied and pasted all of this work, but we replaced the x and the y, then we'd have the wrapping function for 30 degrees, which is pi over 6, and we just have to replace the x value to be root 3 over 2 and replace the y value to be 1/2. So cosine of pi over 6 would be root 3 over 2, and sine of pi over 6 would be 1/2. And there we go. That's the whole thing. So here are the results. If we want to do the wrapping function of 30 degrees or pi over 6 radians, then we get that the cosine of pi over 6 is root 3 over 2, and the sine of pi over 6 is 1/2. If we want to do the wrapping function of 60 degrees or pi over 3 radians, we get the cosine of pi over 3 is 1/2, and the sine of pi over 3 is root 3 over 2. And with 45 degrees, the wrapping function output is the same as the wrapping function output of pi over 4 radians. That's root 2 over 2 as the cosine of pi over 4, and root 2 over 2 as the sine of pi over 4. So I can find cosine and sine for these angles. Now, once I have those three angles, and I know that the cosine and sine values for those three angles, I can project those angles across the x-axis or across the y-axis or across both the x and y-axis to find the wrapping function output for other angles. In other words, think about the quadrants that we were dealing with. I started in quadrant 1. That gave me a positive x value and a positive y value. If I change the x value to a negative, then I'm going to get a point on the unit circle in quadrant 2. If I change both the x and y values to negatives, then I get a point on the unit circle in quadrant 3. And if I keep the x value as positive, but the y value is I put as negative, then I get into quadrant 4. So if the output angle has terminal side that is in quadrant 1, then the sine and cosine of that angle are going to both be positive. If the terminal side of an angle is in quadrant 2, then the cosine is just going to be a negative number and sine is going to be positive. Quadrant 3, cosine and sine are both going to be negative. Quadrant 4, cosine will be positive, sine will be negative. And then we saw earlier what happens when the terminal side lands on an axis. Then either the cosine or the sine is going to be 0. And if we do that projection, I'm not going to spend the time in figuring out all of the angles that we project to. But if we do that projection, then we get this diagram. Notice that we just found the wrapping function point for 60 degrees or pi over 3 radians as 1/2 root 3 over 2. If you project that across the y-axis, then we're in quadrant 2. So the point is going to be negative 1/2 root 3 over 2. And if you do the measuring, that's actually the angle 120 degrees or 2 pi over 3 radians. So that point is going to have give me that the cosine of 2 pi over 3 radians is negative 1/2. And the sine of 2 pi over 3 radians is root 3 over 2. So this is a nice diagram to have and to reference once we've established the cosine and sine of these three angles in the first quadrant. Now, another note that I'm going to make while I'm here, before we actually calculate some other angles, is that if we go around the circle 360 degrees or 2 pi radians, then we are at a coterminal angle. And so since the side is going to be the same, the terminal side is going to be the same at coterminal angles, then the output of the wrapping function is going to be the same for coterminal angles. So while we had 0 radians, we saw that we are at the point 1, 0. When we went around 360 degrees, or another 2 pi radians, we were also at 1, 0. So if I had started at pi over 6, went around another 2 pi plus pi over 6 radians would also give me a cosine of root 3 over 2 and a sine of 1/2. And we could have gone backwards as well. We could have went around the circle in the negative direction. Pi over 6 minus 2 pi radians would have had cosine of root 3 over 2 and sine of 1/2. Now let's go ahead and use that diagram to fill out this table. So we're going to fill out this table. The wrapping function of 2 pi over 3 is what I'm going to be looking at. So again, I just reference this picture since I've already filled it out. We don't have to fill it out every time we do a new problem. We look up 2 pi over 3 and notice that the wrapping function gives us the output, which is point negative 1/2 root 3 over 2. That's something we said just a second ago. So the wrapping function, negative 1/2, comma, square root of 3 divided by 2, which means that the cosine of 2 pi over 3 is negative 1/2. Again, that's something we said a second ago. And the sine of 2 pi over 3 is the positive square root of 3 over 2. All right, there I adjusted my table so that's a little bit wider and it all fits in one row. Okay, so now let's look at the angle 7 pi over 6. 7 pi over 6 is a little bit more than pi. You can see that it is 30 degrees or pi over 6 projected through the origin. So what we do is we take that pi over 6 and we negate the x and y value. And so we get negative root 3 over 2 and negative 1/2. So negative square root of 3 divided by 2, and then negative 1/2. That is the wrapping function output of 7 pi over 6. So the cosine of 7 pi over 6 is negative square root of 3 divided by 2, and the sine of 7 pi over 6 is negative 1/2. In terms of negative pi over 4, we don't have a negative pi over 4 labeled, but we should know that when we take negative pi over 4, all we're doing is rotating in a clockwise direction pi over 4. So that means we are going to be at the same angle. We're going to be coterminal with 7 pi over 4. So we're going to have the same output. We're going to be as 7 pi over 4, which is just pi over 4 projected across the x-axis, projected across the x-axis. So we negate the y value. In other words, the wrapping function is going to be root 2 over 2, comma, negative root 2 over 2. So let's write that down. Wrapping function is going to be square root of 2 divided by 2, comma, negative square root of 2 divided by 2. So the cosine is going to be a negative, cosine is going to be a positive square root of 2 over 2. And the sine is going to be a negative of the square root of 2 over 2. Okay, let me fix that. So there we go. Now, what about 5 pi? Well, if you think about what 5 pi does, we wrap around the unit circle once to get to 2 pi. If we wrap around the unit circle again, we get to 4 pi. And then if we add another pi to that, then we are at the same coterminal side as our angle pi. So 5 pi is coterminal with pi. Therefore, we can see that we are at the wrapping function whose output is -1, 0. We're at the point -1, 0. So the cosine of 5 pi is -1. The sine of 5 pi is 0. And that's it. That's basically how we figure out the wrapping function and cosine and sine for angles that are on this diagram, or angles which are coterminal to ones on this diagram. Here's another table of some angles. I want you to try to push pause on the video and get the wrapping function, then cosine of theta and sine of theta for the following values of theta: 3 pi over 4, negative pi over 6, and negative 5 pi over 3. Again, I'll give a couple of seconds for you to push pause, and then I'll show you how each of these is done. All right, hopefully you tried that on your own. I'm going to do these problems here. So let's start with angle 3 pi over 4. Let's find that on this diagram. That is this angle on the diagram. So we are at the point negative root 2 over 2, comma, positive root 2 over 2. So negative square root of 2 divided by 2, comma, positive square root of 2 divided by 2. And what that means is that the cosine of 3 pi over 4 is a negative square root of 2 over 2. And the sine of 3 pi over 4 is a positive square root of 2 over 2. Negative pi over 6, that is not one that is on the diagram, but it is not labeled on the diagram, but it is coterminal to one on the diagram. If we go pi over 6 in a clockwise direction, then we've went to this angle here, which is labeled 11 pi over 6 radians on the diagram. So the x value is going to be positive root 3 over 2, and the y value is -1/2. In other words, pi over 6 projected across the x-axis gives us a negative pi over 6. And that just negates the y value of the point we get when we have pi over 6. So let's fill that out. Wrapping function of negative pi over 6 is the square root of 3 over 2, comma, negative 1/2. Cosine of negative pi over 6 is the square root of 3 over 2. Sine of negative pi over 6 is negative 1/2. By the way, just as a note, we're going to see this later, but cosine of pi over 6 and cosine of negative pi over 6 were the same value. Sine of pi over 6 and sine of negative pi over 6 were opposite values. One was a positive, one was a negative. Let's look at negative 5 pi over 3. Well, one way is to go around this unit circle in 5 pi over 3 radians in the clockwise direction. 5 pi over 3 radians in the clockwise directions actually gets us back into the first quadrant. Another way is just to take, we see pi over 3 radians here. We could have projected that across the x-axis. And we see that when I talk about negative 5 pi over 3, I have to go all the way around to the first quadrant, and that is going to be coterminal with a positive pi over 3. So negative 5 pi over 3 is coterminal with positive pi over 3. And we get the 0.1/2 root 3 over 2. So the wrapping function of negative 5 pi over 3 is 1/2, comma, square root of 3 over 2, which tells me that cosine of negative 5 pi over 3 is 1/2. Sine of negative 5 pi over 3 is a square root of 3 over 2. Again, that's just from this unit circle. So any angle that's labeled on this unit circle, or any angle that is coterminal to the one of these labels on the unit circle, I can find. I can find the cosine for that angle and the sine for that angle. So that's a really nice thing if I have access to this picture. And again, most of the times we will have access to a picture like this. Even if we don't, we can remember just the cosine and sine of like pi over 6, pi over 4, pi over 3, and then project those across the x-axis, across the y-axis, and across both the x and the y-axis. So obviously that's great for angles that are on those pictures, that picture, excuse me. And with some other angles, there's some special formulas that we could use. We could utilize some triangles. We can use some properties of sine and cosine that we'll see later to find certain special angles exactly if I really want to. But that picture really doesn't help in finding the wrapping function of an angle like 22 degrees, which is 11 pi over 90 radians. So if I'm presented and asked to find the wrapping function of something like 22 degrees or 11 pi over 90 radians, then I wouldn't refer to this circle. What I'd probably do is I'd probably just use a calculator to find the cosine of that angle and the sine of that angle. Now, when you use a calculator, make sure that we are in the correct mode. If we're using degrees, then your calculator has to be in degree mode. If you're using radians, then your calculator has to be in radian mode. For most of my classes, I use a TI-84. And so the mode button is pretty easy to see on there. It's one of the top buttons. And we change the mode from radians or degrees depending on our need. There'll be another video where you can calculate sine and cosine and other trig functions on your calculator. So that's not what we're going to cover in this particular video. I'm not going to cover how to use a calculator in this particular video. But if you want to look that up, you want to figure out how to use your calculator, then by all means, go ahead and look up some other video. Instead, what I'm going to do is I'm just going to find these values using the calculator, and I'm going to describe how I find these, and all of them I'm going to get approximations for. So we're going to find the cosine and the sine of 8 pi over 5 radians. We're going to find the cosine and sine of 13 degrees. And we're going to find the cosine and sine of 10 pi over 11 radians. All right, so all I'm going to do is type this in on my calculator. Now, if I'm using radians, like in the case of cosine of 8 pi over 5, then I have to make sure the calculator is in radian mode. When I do that, I end up with a decimal approximation of about 0.3090. I'll round to 4 decimal places here. We don't have to by any means, but that's what I'm going to do. Now, when I do the sine of 8 pi over 5, I end up with a decimal approximately negative 0.9511 if I round to 4 decimal places. Negative 0.951056, blah, blah, blah. So that's what I end up with. By the way, just knowing that, I know my cosine is positive and my sine is negative. If you think about how that works, well, that means that if you're talking about where we're at, this is the origin, we've moved positive and then negative, positive in the x direction, negative in the y direction. So we are in quadrant 4 with angle 8 pi over 5. That was a little bit sloppily written, but that's what it is. So if you didn't already know that 8 pi over 5 is in quadrant 4, then now we do. And by the way, the wrapping function would obviously be the output of the wrapping function would obviously be the 0.3090, comma, negative 0.9511. Now, if I'm asked to find cosine and sine with 13 degrees, then I need to make sure that my calculator is in degree mode. Again, these are not going to be exact values that I'm going to be writing down. They're going to be approximate. With 13 degrees, I get about 0.9744 for the cosine of 13 degrees. And for the sine of 13 degrees, I get approximately 0.2250 when I round to 4 decimal places. Okay. Your homework may ask you to round to 2 decimal places. It might ask you to round to 3 decimal places. But in this case, I'm rounding to 4 just so that we see what it looks like. Let's talk about cosine of 10 pi over 11. If I do those calculations in degree mode, I'll get it wrong. I need to make sure my calculator is in radian mode. So we need to change back to radians. If I just did the cosine of 13 degrees in degree mode, change back to radians. So cosine of 10 pi over 11 radians is going to be a negative 0.9595. And then sine of 10 pi over 11 radians would give me a 0.2817 approximately. Again, these are not going to be exact values. They're going to be rounded values, but they are going to be points on the unit circle. So if you square this value, square that value, add them up, you should get about 1. You should get exactly 1 if you use the exact values. You should get approximately 1 if I use the rounded values. By the way, we can also see, based on the output of cosine and sine, that 13 degrees is going to have terminal side in quadrant 1, since sine and cosine are both positive. Since cosine of 10 pi over 11 is negative, and sine of 10 pi over 11 is positive, we know we're going to be in quadrant 2 in that case. Negative x value, positive y value. So there we go. We can utilize our calculators to get approximate values for cosine and sine, as long as we're in the right mode. Again, if we're using radians, make sure your calculator is in radian mode. If you're using degrees, make sure your calculator is in degree mode. Mostly on the unit circle, traditionally we use radians because of its connection to the arc length of the unit circle. So that is the end of this video. We've defined cosine of theta and sine of theta on the unit circle as the x value of the point and the y value of the point, where our terminal side hits the unit circle. So we know how to calculate cosine of theta and sine of theta on the unit circle.